So this is the title of my talk, and the talk will be mainly organized around three big chapters. First one is a little history on the origins of life, in particular why this. Second part is why a physicist can be interested in the origins of life besides the intellectual pleasure. And then the third and last chapter will be devoted to how advanced computational methods can be used in doing what is called prebiotic chemistry, and in particular, in our case, to study the Miller experiment on the computer. And the last part will be, of course, devoted to conclusions and perspective. Of course, we are origins of life. It's a big issue, which has been with man since the dawn of time. And we are not going much into philosophy and religious questions. Let's just have a scientific point of view on that. And the big scientific question, at least since Aristoteles, was whether living matter can start, life can start from non-living matter, what is called in modern present day biogenesis, if living matter comes from living matter, or abiogenesis, if living matter can come from inert matter. That was the big scientific question. It wasn't really a question at the time of Aristotle, because he thought that, for example, flies would generate spontaneously from rotten meat, and that crocodiles would come out of floating logs on rivers. So that was the idea of Aristotle, since he was a big thinker. It took almost 2,000 years to counteract, in a way, this point of view. It was an Italian, Francesco Redi, in the 1600s, who was the first one to put, in a way, the scientific method inside this kind of study, because he simply took two samples of meat, one uncovered, the other one covered with something, and the first one would generate flies, the second one didn't. So there was a point in favor of biogenesis. Life is not originating from inert matter, but from living matter. The debate was a big... by then, of course, we were talking about macroscopic life. And a little later, Dutch Van Leeuwenhoek invented the first kind of microscope, which you can see here, which led into this discovery of microscopic life, so bacteria and so forth and so on, and which was a big point in favor of abiogenesis, because nobody could say where this microscopic life could come from. So it was probably spontaneously generated by something.
Is he the first to observe spermatozoids?
No, but he was the first one to scientifically, if I may say, use the microscope to make a connection between the origins of life, whether the life was abiogenetic or biogenetic. And of course, this is the typical subject that took centuries to keep carrying on. There was a heated debate between John Needham in English and Lorenzo Spallanzani in Italian. John Needham said that there was a possibility of having what was called infusors coming out from a sort of boiled broth. But Spallanzani redid the same experiment with much more sterile samples, and he couldn't find any microscopic life. So again, there was a point in favor of biogenesis against abiogenesis. So see Greek, Italians, English, and Dutch. So at some point there's also some French. And it was actually, there was a big debate, we are about 150 years ago, a big debate between Pouchet and Pasteur. And this debate was settled by a big prize. By the time was like, I think, 2,500 francs, even if here I couldn't find only 1,000 francs, but inflation. And a big prize from the l'Académie des Sciences to settle this question. And so the experiment that I think Pasteur did in this very building was to, what he did, he put some boiled broth inside this swan neck flask with this long neck, which would let air inside, so oxygen, but not microbes. And so the broth stayed there with no macroscopic life whatsoever for a time long enough to win the prize, to convince the Academy. And so this was settled, again, against abiogenesis. Living matter can only come from living matter. Of course, we have to keep in mind that by then, we are in the 1860s, people thought that organisms were the same since, again, the dawn of time. And as we know, it was not the case. So at this point came Darwin. It was Darwin who, with his theory of evolution, changed completely the paradigm, because if living organisms can be different today from what they were in prehistory, of course, this opened up many more possibilities in learning about the origins of life. And it was not only the theory of evolution in general, but it was really Darwin, in a letter to Hoover in 1871, the first one to suggest that it might have existed a warm, that's quoting, a warm little pond with full of salts and ammonia and electricity and all sort of stuff, from which life could have been generated, which is what we would call today the primordial soup that you can see here. And of course, we are scientists. We are, very smart, so we don't believe in superstition. But it happens that Charles Darwin was born this very day, 205 years ago. So today is Darwin Day. It's totally chance. And again, so Darwin's point of view completely changed the paradigm, as I said. But again, it took many years to put that from the theoretical point of view to the experimental one. And it was actually two scientists, Alexander Oparin, a Russian scientist, and John Haldane, a British one, who developed separately the theory of chemical evolution. That is, they suggested that, they hypothesized that simple molecules, so water, ammonia, methane, hydrogen cyanide and carbon monoxide, could have interact together in a reducing atmosphere poor in oxygen, and then spontaneously, with some form of chemical energy, develop big biochemic molecules such as proteins and nucleic acids. This idea could never be put in practice by Oparin, particularly because it was the Stalin time. There was World War II, so they had other things to think of. But it was Bernal, right after World War II, who took again a look into Oparin's theories, defended them strongly. It was his style. And so this convinced Harold Urey, who was already a Nobel Prize in chemistry by the time for totally different reasons, to look into it, and so to write a PNAS paper, having more than 60 years, on the early chemical history of the Earth and the origin of life. So there was the one paper who once again settled the theory behind chemical evolution into life. And then it was his student, his PhD student, Stanley Miller, shown here, who proposed to actually simulate in laboratory the early atmosphere, the atmosphere of the early Earth. So by then, they were wrong, but by then the atmosphere was believed to be very reducing, so composed mainly by water, ammonia, methane, and hydrogen. Then, of course, there was a strong volcanic activities and lightning. And so, on this hypothesis, Stanley Miller decided to recreate this condition in a laboratory, so lightnings and early Earth atmosphere, with this little experiment, which I show here. So you have water here, you heat up, water vapor goes here. Here in this recipient you have any sort of gas of simple molecules. So they are put under electric discharge here. They do whatever they want. Then there's a cold trap here, and the liquid matter is recovered here, and then it can be cycled over and over. The original experiment was done in over 1 week, and the result, the important result, was that he found all sorts of organic compounds, particularly, basically all the amino acids, and a lot of glycine, which is the simplest of the amino acid. So in a way, we can say that this was really one of the major breakthrough in science. Same year, Watson and Crick suggested the structure of DNA. And so in a way, this was the single event that redefined the modern research in the origins of life. This experiment has been repeated by Miller and other people over the decades with more and more realistic oxidizing particular atmosphere containing, for example, sulfur dioxide, carbon dioxide, and carbon monoxide. And the same experiment, no, not the same, a similar experiment was performed a few years later by Juan Oro, who managed to synthesize nucleic acids starting from hydrogen cyanide solutions. So in a way, the effect of generating complex molecules starting from simple ones by giving in some way some chemical energy was the major change. So that's when what we call now prebiotic chemistry was born. Of course, and I'll come to that later, I'm really not a specialist, but problem is, okay, we have glycine, for example, simple amino acids, but we still have to move up the ladder of complexity because we need, okay, simple molar molecules to make biological monomers, amino acids or nitrogen bases for nucleic acids. Then you have to go from biological monomers to polymers, proteins, nucleic acids, and we are still far away because then we need to start the self-replication, and so the concept of hereditary, and then there's a big debate which I'm totally incompetent to discuss against the protein world hypothesis versus the RNA world hypothesis, metabolism first or genetics first. That's a big debate in the specialized community. And then, of course, we go into organelles, cells, tissues, microscopic, and then macroscopic life. And even if we restrain to this, to the first elementary steps, which is making biological monomers and then biological polymers, this is really not simple, not a simple issue, and that's where, for example, we have to think of potential sources of chemical energy. That is, which kind of energy can have induced the formation of monomers, biological monomers, and polymers in the early Earth. The first hypothesis is basically Miller ones. You have atmospheric synthesis with these kind of gases, and then you have either electric discharges or ultraviolet or other source of the type. Then you have aqueous phase chemistry, the warm little pond of Darwin, where these guys would interact at larger concentrations, but with effect of temperature, pH, and so forth and so on. Then you have hydrothermal underwater synthesis, where you have higher temperatures, so higher energies, but also higher volatility, and amino acid, for example, can difficultly survive strong temperatures for long times. Then, of course, there's extraterrestrial. Maybe we are all wrong, and all the biological matter arrived with comets and meteorites, and so there's no reason to look into that on the Earth. And interfacial chemistry or mineral chemistry, that is, all the chemistry that can have occurred billions of years ago, but even today, at the surface of minerals, molecules react. They can react for many reasons, for drying, wetting, and many other reasons. So that's an issue we will discuss later. But to give you an idea how complex this problem is, even the simple step of going from biological monomers to polymers for example, to make a peptidic bond between two amino acids, to do that, you have to get rid of a water molecule. You have to make a connection between a carbon and a nitrogen here. So you get rid of water. But to do that in solution is entropically unfavored, is statistically unfavored, so cannot occur on a large scale naturally. So that already this is a big problem. For example, that was the reason why 10 years later than Miller, Fox and Darada remade exactly the same experiment, but they, since Miller's experiment had been criticized for the absence of water, so he tried to make the same experiment in ultra-dry conditions, in which he put on top of Miller molecules and electric discharges some silica and other materials to simulate really the very dry condition inside volcanoes. And then, at the same time, again, the same Bernal suggested that actually the biological polymerization occurred mostly on the surface of minerals, which has been dubbed polymerization on the rocks. And so in a way, all this part, just to tell you that I wouldn't say we have no idea, but still there are many, the origins of life can be extraterrestrial, meteoritic, submarine, ultraviolet, mineral, or basically all of the above. And the respective, again, I'm not a specialist, but the respective ratios are very difficult to estimate, not only now and in the early Earth. So that's, I mean, I have no more answer than this on the origins of life, which leads me to the following question: why are we here? Of course, we can think of this question this way: why are we here? From the religious or philosophical point of view, but I'm much more earthly than that. Why are we here today in this physics department, which is what it will look like after the works, by the way. Now, why are we here? Particularly, you're very nice to be here. Why am I here? I'm a physicist, a solid-state physicist. So why am I talking about the origins of life? And we come to the second chapter, because we physicists, we think that we are very smart, so we can take whichever problem. We can take a dinosaur and study its electronic wave functions, and then go back to dinosaur and pretend to have the solution. So that's precisely why we are here today. In particular, again, Miller experiment was a matter of philosophy in a way, but biology, earth science, and chemistry. Where does physics come into play? Of course, we can take here all the scale, from blood vessels and whatever biological elements to molecules. Again, here we have big molecules, and in this scale I found we'll go straight to atoms. So the point is, Miller experiment in 2014, work done last year, so that's why it's not 2015. Can we retrace it step by step, starting from fundamental physics? To do that, we have to answer a few questions. We have to ask ourselves a few questions. First of all, what causes Miller prebiotic reactions? There's certainly an effect, a potential effect of temperature, which is easy to check. And if you just take your Miller molecules, just heat them up, you don't get amino acids right then. There certainly is an effect of ionization, which is very difficult to treat in the kind of calculations we do, so I'll just say a word about that. And then there's a potential effect of the electric field, which was precisely the point we wanted to take with my coworker, checking whether the electric field by itself is capable of inducing a Miller reaction. Again, that is easier to say than to do, because to do that, first of all, and then we come to physics, we have to solve the many-body Schrödinger equation for the electrons in our system. Then we have to use finite temperature method to properly explore the phase and reaction space. And then, in our case, this is general to any kind of ab initio simulations, if you want, But in our case, we also need to apply an external electric field, which is not that easy. So again, I'm not making a class on ab initio calculation because I think that most of you know what they are. I just say that ab initio calculation means solving exactly a quantum mechanics fundamental equation for many body systems. This is, of course, a historical problem with many developments over the decades from Slater, Hartree-Fock, and basically the branch of chemistry is known as quantum chemistry, is all a post-Hartree-Fock development with many different names and many different approaches, which is very, very accurate, incredibly accurate. Point is, if you go on Web of Science and you look for prebiotic with any of the synonyms, typical synonyms, of course you get like 50,000 hits. If you look for ab initio and prebiotic, you only have 115, and 35 are from last 2 years. So why? Why is that? Because quantum chemistry calculations are incredibly costly. So even if there's a very nice paper which I really looked into a couple of years ago, 2010, if you want just to study, for example, how glycine forms on ice water dust mantles, which are typical interstellar dust particles present in the space and on Earth, you can only just take a periodic solid. You have to make a model, a cluster model of the system, fix all atomic position, and with incredibly costly calculation at fixed geometry and whatever, you finally end up with a number which can be fully relaxed or partially optimized. So many costly calculations in a very, very specific case. You have to guess by yourself which are the chemical reaction paths. You have to do hand by hand, little by little. It's just that modern methods are not enough, because that's really one of the very few works based on ab initio quantum prebiotic chemistry. Again, we are not chemists, we are physicists, so we can count on Walter Kohn, who developed in the 60s the so-called density functional theory. Density functional theory is intrinsically less accurate than all the quantum chemistry method, but it's much more efficient. I'm not going into many details, but the key point of density functional theory is that if you study the system not in terms of electronic orbitals, but in terms of electronic density, n, so you can write the total energy of the ground state total energy of the system as a functional of the electronic density, and then with a complex mathematics, you can map this system into a simpler system with the guarantee that as long as your electronic density is the closest possible to the real electronic density, the system gets towards this minimum because the theory is variational. So if you have test function that approximate better and better the real problem, you approach closer and closer the electronic ground state, which is at the basis of any variational theory. This is, this was enough for Walter Kohn to get the Nobel Prize in chemistry, not in physics, in 1998. Again, this is good to treat large system, but if we are still bound to zero temperature, because the theory is entirely developed with no temperature effect. So that's where smart finite temperature effect developed by fellow Italians in my alma mater in Trieste, Karen Parinello, developed in the 50s, which was the basis of ab initio molecular dynamics. They are two perennial candidates to the Nobel Prize in chemistry. Hopefully one day they'll get it. And for example, putting temperature and DFT in this kind of calculation was the reason that motivated this paper, this nice paper in Nature Chemistry a couple of years ago, in which they could take the Miller-like soup, simulate the impact of a meteorite that is a strong gradient of pressure and temperature, and then a relaxation, so heat and compress here, and then cool and expand here dynamically. And this was a key to find, for example, glycine and other complexes which justified this nice paper. One of the very few examples is this paper that Dominic Marx and co-workers, in which they simulate the formation of the peptidic bond between two glycine molecules at the surface of a mineral, again using temperature in the Carparinello fashion on top of density functional theory. So we have a couple of tools, but still we need to apply an external electric field. And doing that, even within the very smart density functional theory, is not easy, because density functional theory is entirely based on periodicity. It's developed theory based for the electronic part on crystal systems. So everything is periodic. You have a unit cell, you have plane waves, you have block functions, and you have a lot of reciprocal space, which of course is the smart way to do when you have to treat simple solids. When you have to extended solids, still you rely a lot on periodic boundary conditions. And when you do ab initio simulation of liquids, in a way you are bound to have a liquid in a large enough unit cell, but then this cell is repeated periodically, which is very good in general, but is very difficult for electric field. Why? Because to put electric field into electric field is unbounded, it's just a straight line. So if you want to combine that with periodic boundary condition in an easy way, you put a sawtooth potential, which is okay when you have a low-dimensional system. We did that with co-workers on graphene with no problem. But then if you have a bulk system, this is unphysical, and it's not just a technical point. It is unphysical because the definition of the position operator in a periodic system is not trivial at all. It is related to the Berry phase, developed in 1983. The Berry phase theory of polarization was developed by David Vanderbilt and from Rutgers, Raffaele Resta, again from my alma mater in Trieste. And with very smart mathematics, they proved mathematically that the macroscopic polarization can be expressed as the imaginary part of the logarithm of the determinant of a particular operator, in which the position operator is expressed, can be expressed in a periodic system in a totally correct and rigorous way. And so this becomes quite recent, because this theory was implemented in a ab initio molecular dynamics code only about 10 years ago, and that's the tool that we used in the following. So now we come to the third and last part of the talk. What can we do with all these tools? What can we do to learn a little on prebiotic chemistry? So again, a reminder is, the goal is we start with simple molecules in an aqueous environment, like typically water, ammonia, methane, hydrogen, or other molecules. We try to put them in to simulate just a part of Miller experiment. We try to put them under some sort of electric field, and then we hope to find at least glycine at the end of the road. Again, Miller experiment was performed more than 6 years ago, so there's a theory, chemical theory behind Miller experiment. For example, when they looked at the rates of products in Miller experiment, they found that there were a lot of aldehydes and hydrogen cyanide as intermediate products in a time scale here. I don't, for some reason this is Italian, but it's a time of few hours, several tenths of hours. And so there's these reactions were traditionally explained via the so-called Strecker mechanism, which is shown here. Again, I'm not a chemist, so I know as much as you do about this, probably less. But again, so the key point for us is probably to go from water and methane to glycine, we need to go through these intermediates. So through these, at least formaldehyde and hydrogen cyanide. So as any good scientist would do, I went on Wikipedia, I looked at Strecker reactions, and I found out that the first step of Strecker reaction, you have formaldehyde, hydrogen cyanide, water, and ammonia and water. You have some intermediate product, and then this intermediate product can react to make up again ammonia as here and glycine like here. So I say, okay, I thought that Wikipedia was enough. And also because there's a problem which is not just technical, but in our simulation, we really need to work as much as possible with a constant number of particles. So even if we really want to make up supercell of simulation with all the ingredients discussed above, which were already from the start compatible, at least already from the numerical point of view, with the predicted Strecker reaction. So in the Strecker reaction, the ratio in these two intermediate and final step, the ratio between CO and NH is 1 to 1 to 1 to 4. So we said, okay, we try to build an initial cell containing exactly this proportion of atoms, and we got inspiration from the last paper Miller published on PNAS in 2002, a few years before he passed away, in which he insisted much on the presence of carbon monoxide, which is an oxidizing agent, which make this atmosphere much more credible than the initial atmosphere he had used 50 years before. So, this is a very simple elementary school mathematics. We developed an initial mixture with 8, 8, 8, 5, and 10 of each of these molecules, water, ammonia, methane, nitrogen, and carbon monoxide. We took a different cell with the Strecker intermediates, 9999, we have the same number of atoms, and then a final cell, 3 different systems with the products, again, in a way to respect the same proportion. And the idea was that we let the first starting mixture evolve in time. We let separately the second, the intermediate step evolve in time, the third one, and then at some point we can put the electric field and look whether the first one falls somehow into the second one and the second one into the third one. So this is just technical details. The important part here is that we still deal with very little systems. Again, we have few tens of molecules, a little more than 100 atoms, picosecond trajectories, work at constant temperature and density because it's easier, and our electric field are of the order of 0 to 0.5 volt per angstrom, which is very much, but again, I'll show you later that it's reasonable.
What means 20 to 50 picosecond trajectories?
That each of these, the cumulative trajectory, basically we start this system, we put them in a canonical ensemble with constant temperature at constant volume, and we just, calculating the electronic forces with, on top of that, the electric field, if we put the electric field, then we integrate the equation of motion, Newton's equation of motion, basically, and then the system evolves, and since the interaction forces are only due to the electronic part, if the system wants to make a new molecule or break an old one, it's totally free to do that. In this sense, we use the word ab initio. We don't guide the system to do anything. It's the system that does what it wants. Of course, the difficulty is that we cannot afford more than picosecond trajectories because we need to sample the trajectory with a very fine sampling. And so we only have access to short trajectories, and this is a problem to have a full vision of the free energy landscape, which I'll come in a minute. So then it's easy. We start with Miller molecules, no field. The final step, no field. So this is just everything is neutral. Then the intermediate step, and we found that the intermediate step has a higher potential energy than the initial system, which is not a problem in geological times, but this is a problem in a small system. In a short time, we will never get enough statistics to overcome a higher energy. And also it tells us that maybe this intermediate step, this supposed intermediate step, maybe there's something into it. Then again, with no bias whatsoever, we then put our molecules in a strong field, hoping to find formaldehyde and hydrogen cyanide. And instead, we found 2 different molecules, formic acid, shown here, and formamide, molecules I'd never heard before, which is now probably the word I pronounce most of the time in my research life, so it's a new friend. And I'll show you just a little movie of this reaction. I took off all the other molecules. So you have to imagine this box is filled with other molecules, but they are interacting all the way, so they hinder the view. So I only put the CO molecule, the NH3 molecule, and the formic acid, which has already formed before. And just to show you that just solving the density functional equation of motion with the electric field, at some point you have a CN bond which forms, and a formamide molecules here, a formic acid here, and another proton which has disappeared because it's been taken by other water molecules of the bath. This is nice. We find formamide, a new molecule, at least in our Miller picture, but finding one is not enough because we want to be quantitative. The problem is having a quantitative thermodynamic point of view on, in general, in particular in chemical reactivity, is not an easy task. That's another major step by my good friend Alessandro Laio and Michele Parinello, again in Trieste. It's an advanced method of thermodynamics which is called metadynamics, which I'll show in a second, just a sketch. Basically, you want to study a given system, and you want to explore, in particular, the free energy landscape, which again is not, of course, the potential energy landscape. The metadynamics method basically is a method that helps you to overcome kinetic barriers, whichever the reaction coordinate might be, and go over barriers which are much larger than the thermal barrier. In a way, you can imagine of having a given system in a given reaction space or configuration space, could be even a solid-solid phase transition. If you call P the probability of the system to populate these three states, A, B, and C, if the system, you have explored the system long enough for a macroscopic time limit, you can obtain the free energy of the system with the barriers and whatever just from thermodynamics, from statistical mechanics and thermodynamics. Problem is that it's not that easy. And metadynamics is a relatively new method which allows you to, basically, you identify a reaction coordinate, which is a tricky part. It could be a distance, it could be an angle, it could be a topological variable. And every time you visit that state, you just lay a Gaussian. And so you feel, in a way, what is called a history-dependent bias potential. You feel the potential, the free energy well in which you are, and then little by little, feeling the system is pushed up and upward. At some point, it may fall into a different minimum. And then if you equilibrate the system long enough, you can visit back and forth. In a way, just summing up all the Gaussian you have laid over your trajectory, you change the sign, and you get the free energy landscape of the system. Simple. The big problem is just to find the right reaction coordinates. There's an expert in the room, which I'll mention later, and it's not me. For our Miller case, okay, we found formamide. We tried to have a quantitative data on this formation. So formamide basically sits in the middle between CO plus NH3, or the breakdown into water and hydrogen cyanide. So we took a different unit cell. We put just these two molecules in a water bath, and we just took the CN distance as reaction coordinate. Again, this is a very abrupt approximation, but we just wanted to compare the barriers and the energetics of this reaction with or without field. And we found out that without field, you have an energy barrier of about 63 kilocalories per mole, and a minimum which is slightly lower, which is coherent with known data. The electric field dramatically lowers the barrier and dramatically lowers the minimum of formamide, so favors the formation of formamide with respect to the initial reactants. So this was good enough. So we decided, rather than following the historical Strecker reaction, we decided to put more of our spontaneously homemade molecules, which are formic acid and formamide, we put this system into with strong fields, and this paid off because, again, I don't show all the other molecules, but you have here a complex reaction here and then here, in which a sort of formic acid forms here, and then a carbon-carbon bond forms here, and you end up with an amino acid which is not glycine yet, because you have an OH group here, which is called hydroxyglycine. Then you let the system evolve a little more, and at some point this oxygen group leaves, leaving a proto amino acid which is still have a single bond here, a double bond here rather than a single, so it's not glycine yet, it's dehydroglycine. Again, names for which Wikipedia is very useful, because I have no idea what they were. And the final part, you guessed it, at some point we ended up with glycine, that is two dehydroglycines together. At some point one of the two grabs the hydrogen of the others, and so you make up a full real glycine at the end of the road. So, in a way, we have been able to reproduce step-by-step Miller experiment. Problem is, and that's the part which has been strongly debated and I wouldn't say controversial, but still it's a serious issue I learned later in the community, is formamide. Formamide is not observed in the as final product of Miller experiments, but then again, in our simulation, we see it only for a very short time, a few picoseconds, even less. So it's not surprising that on the macroscopic time scale it's not observed. And then, so key point is again this double reaction, formamide into this side or this side. And then going through the literature, I found out that formamide is been known to make glycine under electric discharge. It was a recent study of 1913. I don't read German. I don't know if Werner Kraut is here to help me, but I can find here, I see here formamide, I see here glycine, and as far as I've been told, probably Edouard can say something in German, this says that the formamide under electric discharge actually makes glycine. So first of all, its result was known 40 years before Miller. Then there are people very much into the origins of life who suggested recently that formamide is actually the hub, the chemical hub to form nucleic acid. This is known, carboxylic acid and also amino acids. And in fact, it's involved in the so-called missing G. Formamide is necessary to form guanine. You can do the other DNA bases with other chemicals, but to do formamide, to do guanine, you need so far to have formamide irradiated with ultraviolet light. Marie est partie, but I know that formamide is very abundant in protostars, so it's also an extra very much found chemical in the stars. And to comfort our hypothesis that the same simulation discussed a little ago, they found as intermediate formamide and formic acid. And even this is an experiment in which they simulate in laboratory the impact of meteorites. They basically take the primordial soup and they fire bullets at it. So they don't kill life, they make life apparently, or at least they make amino acids, and they find formamide as an intermediate. So we think we are not too far away from truth. And later, one month ago, there was this big paper of exceptional significance by a Czech group in which they put formamide at the center of prebiotic chemistry. And actually, these guys have called us to ask us to suggest them the best mixture to heat with their lasers and make interesting chemical stuff. So, where are we now? We are very much into the full-fledged quantitative study of metadynamic study of this prebiotic chemistry. This is a live making of the free energy landscape in the breakdown of formamide into carbon monoxide and NH3. So this is, of course, this pictorial because you need much more work to do that than what you see here. And also the breakdown into water and hydrogen cyanide. With our method, we can go through all the isomers, the transition state, an intermediate state, another transition state here, and then the final result. So this is very much work in progress, which leads me to perspectives and conclusions. Perspective, this is the same picture I showed before, and the important part for us is this one. Mineral surfaces are very important in the early Earth and are still important now because we still have Earth and minerals in present-day Earth. And mineral surfaces do have natural electric fields at their surface just because they're a surface. That is, it is known that surfaces have a nanometric, even less, electric field. The hypothesis, the long hypothesis is that this electric field is not important because it's in a solution. It is immediately screened by the so-called double layer, which means that the electric field is strong in a short, over a short length, but then it fades away. But still, this part where the water-mineral interface, where there is strong, natural, not induced by Miller, electric field can be interesting. That's where we are working on. This is a simulation which we put MgO surface and water, and we plot here on the right-hand scale the averaged local electric field on this component, and we see that the electric fields are of the order of a few volt per angstrom. They are very short-ranged, but they are a few volt per angstrom, and which means that, not surprisingly, we see proton hopping and other chemical phenomena which we know can be induced by the electric field from our different bulk simulation. So what we are working on is to study a surface field-induced Miller chemistry. For example, now we are studying a CO molecule here to see whether it can form formic acids, and so whether to be quantitative on natural electric field, which are in a way more interesting than a Miller idealized case of simulating lightnings. So I almost come to my conclusion. This is the part of my talk in which I would turn to young people in the room and saying that if you do research in science, you cannot really predict what the outcome would be. In my case, this was madness in a sense that there's been, I mean, there are people here who are certainly used to have big media and headlines all over the world. I wasn't expecting that at all. This is very nice, but there's no way to predict it, just really rigorous and hard work. Point is that I say madness in a positive way here, but madness can have a different meaning, because if you Google my name and Miller on Google, between the probably 10 to 15 first hits, you find one of the many religious sites which cite my name. One of these is Creation Evolution headlines, which is interesting because they say that Miller was Frankenstein. They say that I am breathing life, new life into the old icon. They say that we are liar, milking it, or propaganda, atheistic materialism, so we need to debunk the useful lie. And the final sentence is, help stop this scientifically vacuous, emotionally poisoned propaganda from doing any more damage to impressionable minds. Again, up to 55 days ago, I would smile. I did smile about it. Right now, I think that we only have to put the picture of the Marche Républicaine, because I think that in a way, I mean, I don't feel at all that I'm threatened personally, but still, it's disturbing that this is really disturbing for me, especially in the wake of what has happened in the last month. I come to real conclusion now. So I hope that might have convinced you that ab initio metadynamics with topological variables can be a really powerful theoretical and computational approach, in particular, in our case, for ab initio Miller experiments and ab initio prebiotic chemistry. In the specific case, we identified formamide as a key prebiotic compound, and we learned that this was not settled and is now a heat debate. There are, of course, many other open questions, in particular, this role of natural surface fields in chemistry and reactivity, and more general, whether electric field-induced chemistry, which is, in my point of view, a totally new issue in this perspective, can be interesting in the synthesis of old and new materials. So I would like to thank, one thing that is good with science, that it allows you to work with anything, anybody you want. So I'm very glad to have done this work with my childhood friend, Franz, in my hometown in Sicily. That is great about science. And I want to thank 3 persons, 2 of which are in the room. François Guyot, who is a professor, a former Normalian professor at the Muséum National d'Histoire Naturelle, who guided me all over the way. He's a world-class geochemist who knows much more than I do about this stuff. Fabio Petrucci is also back there. He's a new Maître de Conférence in our group, very young, very bright and brilliant young guy. It's my golden boy. And Rodolphe, another former Normalian, who's professor in the Department of Chemistry of École Normale Supérieure. And there are many people involved in the future outcomes of the work. There are 2 students, two of my students, which I like to mention here, Giuseppe Cassone and Sara Laporte. And I thank the department for inviting me here. Thank you.
Okay, thank you for this very nice talk, which gives a nice summary of the complexity of this problem on the scientific and societal side. Any questions? Use the mic. If you have a question, please use the microphone.
The effect of the electric field, of course, will polarize the molecules that are present. Isn't that the basic effect that's going on? In other words, you are modifying the potential energy surface in that way.
Yeah, I think that's precisely why we are trying to look into it with really more powerful and quantitative tools, which are behind this metadynamics approach. Of course, the electric field does modify the potential energy landscape, and I think that somewhere there's also an even deeper effect. That is, electric field, maybe I'm wrong, but my idea is that the electric field is a vectorial field. So in a way, in privileging a direction, it opposes entropy, in a way, which, besides putting dipoles aligned because of the electric field, also intrinsically favors the emergence of larger molecules, less entropic systems than disordered ones. In this case, of course, CO, which is CO, NH3, water, are all polar molecules, so they are definitely sensitive to the electric field.
I'm surprised that you pay so much attention to electric fields superimposed on an isotropic space, because most interesting things in chemistry happen at surfaces, at interfaces. You mentioned that several times.
Yep.
There are silicas, of course there are also proteins which act as enzymes, and that is the ultimate surface, but even more primitive surfaces, prebiotic surfaces, like pieces of clay or rock or whatever. There's much more chemistry going on the surface of clay than in any isotropic volume that you can imagine, with or without electric field. So I would strongly suggest that you include some sort of surface model in your whole story.
That's precisely what I showed here. I'm glad that you say that, because, let me explain beside the madness here. That's precisely the point. Again, I go back to the roots. Why am I studying the electric field in the bulk? For me, it was really just a game. And again, this is one of the nice parts of being doing research, that sometimes you can play a game just for the sake of your intellectual pleasure. So the idea, we had the machinery. There's a part I didn't show you, which is the electric field applied on bulk water, on which is my specific domain of research, in which we have nice and interesting results. At some point, with my friend, we said, okay, why don't we try whether the electric field, the bulk, idealized, unreal electric field, can play a role in Miller experiment. Actually, the full story is that we were watching the same TV program, probably it was National Geographic channel, him in Italy, myself here in France, and the next morning we said, oh, we really discussed starting from the, say, why don't we try it? So the idea was really a proof of concept, whether the same machinery we built up for simulation of bulk water, which is still my main goal, would apply to Miller molecules. Of course, took a long time and much more effort. Again, the reason why I insist here on minerals is because Miller bulk electric field is useless, is an exercise of concept, a proof of concept. What we are really studying right now is whether the natural electric field at surfaces can play a role, and again, with the appropriate thermodynamics tool, we can separate the electric field from any other contribution, which is oxidation reduction, which is steric concentration. That's why we took MgO surface, which is not a real an important mineral, which has the advantage of being a perfect, in real life, in experiment, it's a perfect surface with no reconstruction, with no pathologies whatsoever, so we can really single out the effect of the electric field on, in this case.
Is there a general explanation why nature progresses along this ladder of complexity? Because as you mentioned, it doesn't stop with these biopolymers, but it goes on and on. So can you understand it maybe thermodynamically?
It's a difficult question. It's a very difficult question. Again, I'm not an expert. What I understood is that the key point is, which of course has also philosophical implications, the key point is whether at some point the local environment provided by big molecule is favorable from the chemical point of view to make a copy of the same molecule, to favor the formation of exactly the same bonds as the initial one. This is, which is the basic of hereditary and genetics. I think, again, it's a very complex problem. You have many, many terms that come into play. Honestly, I mean, my answer is as good as yours, or even less. So do give me an answer.
A naive question. In your potential energy landscape, you can go over the barrier either by thermal activation or quantum fluctuation. Which one is dominant? Do you really need a quantum calculation?
The quantum calculation is necessary in ab initio molecular dynamics. Typically, we treat quantum, in a quantum way, the electrons. Because otherwise, we have to rely on models, on handmade models, to describe the interaction between atoms. Then the atoms, they are classical. They are solved with Newton's equation. So to fill up, for example, a free energy potential well, the quantum part is only on the electrons, is only on the forces acting on atoms. Once you have that, if you, in another way, you can use free energy sampling and metadynamics either with ab initio molecular dynamics or classical molecular dynamics. Once you have the forces, the dynamics we do is exactly the same. The quantum part is for the electrons. The only little point is the hydrogen. The hydrogen is so light that it can have quantum effects, and treating the nucleus as a quantum is very tricky, it's very complicated, it increases your calculations of orders of magnitude. And in our lab, we're actually thinking of ways to overcome this because it's a big issue. But in these problems, at these temperatures, we estimate that quantum effects are on the proton are not the most important part given the complexity of the problem.
Yeah, am I wrong in saying that you apply the electric field instantaneously and you suppress it instantaneously? So does that change it? No? No,
it's a constant electric field. Constant over a time window of a few picoseconds.
Okay, so you do your simulation with a constant electric field.
Okay. That was the difficult part in a way which took from Berry phase theory in 1983 to macroscopic theory of polarization in the 90s. to the implementation in real codes in 2002.
So I was wondering, if you have a surface where there is a high electric field, are not the molecule going to be stuck to the place where the field is high and stay there after they have been synthesized?
That's molecules at the surface. Surfaces do many things, including being stuck and then again go away. And the advantage of having a topologically powerful method as metadynamics is precisely that you can at some point force the molecules out of their potential well. But in doing that, you are measuring how deep this well is. So you are actually reconstructing your free energy landscape. That's a very good, legitimate question, which we are actually looking into it right now.
Okay, I think we've run out of time, so let's thank Marco again for this very nice talk.
Thank you.